Stat students. So today we're really going to be going through the last lesson of this unit. I know this unit feels very quick, but it is pretty quick. It's not a ton of topics, but the topics that we're going through are extremely important, so it sort of deserves its own unit. So we've been learning about sampling distributions. We talked about proportions when we looked at the Reese's Pieces machine. That was sample proportions to estimate larger probabilities, larger proportions. You have problems that you can work on to get some extra practice with that. There will be another Delta Math that's coming out soon to get just more practice. So be on the lookout for that. But we're going to be talking about sampling distributions of sample means. Okay, so let's go ahead and get started. The intro. All right, so let's go ahead and get started. So in your notes, draw a line and write sampling distributions of sample means. That's what we're going to be talking about. So we kind of want both of those, sampling distributions of sample means. All right, and we're going to start with an activity today. And we are going to be talking about the Gettysburg Address. Okay, so I have pulled up the Gettysburg Address on here, and you guys will need your calculators, so go ahead and have those handy. Have that up. You're going to need a list and spreadsheet. Okay, just have that handy. And I'm going to pause it. And what we're going to be doing with the Gettysburg Address is you are going to be picking 10 words from this address. All right, I'm going to actually pull up the instructions for you. Okay. From the Gettysburg Address, you're going to select a representative sample of 10 words. After you get your 10 words picked out, so however you want to do that, you're going to pick 10 words, whatever they are, and then you are going to count the word length, each word length. Then you're going to calculate the average word length of your 10 words. So you can do that in the calculator. As you find the word that you want to put, you're going to put the number of letters in that word in here. You should have 10. Then you're going to calculate the mean, okay, the mean word length. So I'm going to pause and let you do that. I'll have these instructions repeated on there, exactly what you need to do. Hopefully there's not much confusion to that. Hopefully you guys do a pretty good job, okay? So I'm going to pause. All right, so you've had hopefully enough time to pick 10 words, take their word length, and find an average. So now I want to know what is your average. So you're going to submit in this next pause, what was the mean size of the words that you found? Okay, so tell me the average word length of those 10 words. All right. Okay, so you submitted that. I'll look at those later. I do have the example that we did in class. So this is from my third period. Here is the distribution. So we're just looking at the actual sampling distribution itself. This one was 4.3 right here, and this one is 7.9. Okay. So I'm going to be drawing on this, and if you want, you can copy down this distribution in your notes. This is for my third period. You can add your dot to that distribution. I'd actually recommend that you do that. Okay. I'd actually recommend that you do that. So actually, I'm going to pause and say copy down this distribution. You'll notice it goes from 0 words to 11, I think I have over here, because I think 11 is the longest word. Okay. And then what we're going to do is we are going to calculate the mean of this distribution, which is what I have on this slide. So yesterday when I did this, we got a mean sampling distribution of 5.75 for the average. So I'm going to draw a line here. So we're going to let me insert a line. Okay, and it can be blue, that's fine. 5.75 is what we want, and I'd like you guys to draw this line as well. So probably about right here. And then I'm going to draw on this, and we are going to call this the mean of the sampling distribution of X bar, okay? The mean of the sampling distribution of X bar, so we have that. So this is the center of our distribution, and for the Gettysburg Address, if we look at it again, we are saying that the average word length is 5.75, okay? So, did we do a good job? That's the question. there were some concerns in my third period class that, they felt like they didn't actually pick the words from here properly, and that their sample wasn't as representative as they could be. So I asked the person who had the shortest amount. I said, how did you get yours? This was 4.3, and they said they just took one sentence that had 10 words, and they went with the world will little note nor long remember. Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they stopped here. That's how they did theirs. That was their 10 words. Okay. So do we feel like this one sentence is representative of the whole thing? Well, maybe not. Then I asked the student who had the 7.9, I said, how did you get your words? And they said they picked words that sort of had meaning, and a lot of them were longer words, right? And so you think about the sample you took. Did you do that the same way, right? Did anybody pick a one-letter word, like the letter up at the top here? Did you pick, we have a new nation. Well, do you consider that to be a word in your sample? Because it technically counts as a word. It's one letter, right? So, you have to think about that. Did every word have a chance of being picked, right? So, what actually happens here, and I'm going to pull something up here. So this website here, this is the same applet where we used the Reese's Pieces. Here is the distribution. This is the population distribution for the words in the Gettysburg Address. So look at this. It has the distribution, the counts, and there's 268 words in the Gettysburg Address, so 268. And we can see that the mean is 4.295. So let's go back to our slide here. And I'm going to duplicate this line. I'm going to change its color. The shape, let's change it to, let's make it red. Okay. And we get 4.295, so that's probably right about here. It's almost exactly on this one student's point. And that is the true mean. So we have mu as the true mean value. Okay. So what we see here is an example. Hopefully you remember the phenomenon that's actually happening here. What we see here is called bias. This is how you have biased estimators. This sample that we took is not a good sample, right? Because we didn't actually take a proper representative sample from the population. We just picked words. So this activity, like this example here, is the best example that I think you've ever seen of how bias can happen in samples, where we're not able, or when we don't sample properly, we get results that aren't very good. So going back to this is our penny example where my class took samples of pennies. Okay. And we talked about how, the idea of bias here, and we said the center was here. And so if this red line is our mean, like the true parameter, then we have some bias up here in this top distribution. But this one would not. But what if the true mean of the pennies was this green line right here? Well, then we do have bias. So I want you guys to look at this. This applet also has the pennies. So we're going to talk about that. So pennies. Here is the distribution of age of pennies. Okay, and you'll notice that it's harshly skewed to the right. This means that there's more youthful pennies than there are older pennies, which makes sense, right? And look at the mean, 12.26. 12.26. So if I go back here and I draw again, 12.26, let me insert let me go here. I'm going to insert another line. So we'll go 12.26, draw this all the way down, make it vertical, slide it over, and make this a little bit thicker, and a little bit more. Okay. So here is really where our line is. So you can see that our distribution is extremely biased. Okay, because all of these coins are coins that I've just gathered over the years. You're never going to lose the older coins. In actual circulation, So that's why this makes sense. In actual circulation, these pennies are going to either get recycled back to the treasury, they'll be lost, obviously, and never found again. And they sort of, so that's what's actually happening here. But I have pennies in that bucket that there's some from the 60s that are never going to, they're never going to leave that bucket. So we have bias in my sampling. Also, the samples weren't perfectly random, the ones that were done in class with the pennies. But so that's what we're seeing here. And that's this idea of bias and how that can throw off our estimates, because these samples, every dot on here is supposed to estimate the true parameter. Right here, every one of these dots is supposed to estimate the red line, but it does a bad job when there's bias. Okay. I absolutely forgot to put the next distribution up, but here's what we're going to do. Okay. We are going to actually take a proper sampling of these words, and you're going to do this, okay? So you're going to repeat what you just did, which was you're going to take you're going to find 10 words that are representative. So how are they going to be representative? Well, I have this spreadsheet here that you're going to use, okay? I'm going to upload it inside of the PlayPosit, so you can download it or view it however you want. But you're going to grab your calculator, get 10 words. So how would this work? Well, there's a couple ways to do it. Okay, you are going to type in the function randint. Okay, if your buttons are broken for some reason, you can actually go to the catalog here, type the letter R, and then go down to randint. So let me show that again. The catalog button is to the right of the number 9. It's this little book. Okay, if you type the letter R, it'll take you to the R's, and you can go down to randint. Okay, and we can do this. We can do we're going to pick a random integer between, and we look at this, how many are there? Well, there's 268 words, so it's between 1 and 268 comma 268, and you can generate these one at a time. Okay, or you could do this, which is you can put 10 and it will generate 10 words for you. Okay, here's the problem though with this. If you remember from our very, very first unit, these calculators are all reading from the same row of random digits. So what I'd like you to do is press enter a few times on these. See how I'm doing here? A random amount of times, and get a random row of these digits. Okay, now notice how this sample is not going to work. Look at this. We have a repeated word. We can't have that. So if you end up having repeats, so check your rows to see if you have any repeats. If that happens, you're just going to have to do it again, okay? Until you get one that doesn't have repeats. So this would be a good sample. So I would go through my list. So 219, I'm going to go find 219. 219 is the word the, not a word we would normally pick, but you're going to record that, and you're going to put that into your list. So I would put 3 in here, and I'm going to repeat that process. I'm just going to go through all the numbers that I had, okay, and I'm going to find this. So my next one would be 143, which is little, so that's 6. We can hit escape, so that's 6. Use this again. 180, which is here, so that's 4. So you're just going to make your own sample. So go ahead and do that, okay? All right, you had time to find your random sample. Go ahead and calculate the mean of it. You need to make sure you calculate its mean and compare that to the actual mean, this red line. Okay, is it close? Is it better? And I can guarantee you that if we made a new dot plot, and this, I forgot to put the dot plot in class, or from class in here, which I feel very bad about. But it would shift over. All these points are going to be shifted over, and they are actually going to do a better job of estimating this red line, okay? They're going to do a better job of that. So I'm going to have you go ahead and, just like you did last time with the last mean, submit your new mean. Hopefully it's spot on or very a lot closer than what you originally had, okay? So go ahead and submit that for me. Okay, so let's go ahead, and I want to talk a little bit more. We're going to do some examples over here. We're going to talk about some of the properties for sampling distributions of sample means, and then we're going to work some questions. So we're going to go back to the Gettysburg Address scenario, and we're interested in word length. And what we're going to do is we're going to do exactly what we were just doing ourselves. We are going to take random samples of size 10, okay? And if we do that perfectly, so just like you did, one sample of size 10, they're all going to be random words. What we're going to see is, if I draw one sample here, we have our population over here. The blue dots show where it picked the word from, okay? Here is the most recent sample distribution. And then this last one is the sampling distribution. This is the mean of this. So our mean from the last sample was 4.2, okay? So you can see that here. And so we only have one. So it was a 4.2 is the mean. That's pretty close to the actual mean, which is 4.29. So it should be better. Let's do another one. Let's actually do as many as what was on the slide. Okay, so there we go. So this is the new distribution of these sample means. So this is a sampling distribution. You can see the mean of it is 4.077, which is a lot better than what we had when we were doing bias sampling. The mean was 5.75. So it is more accurate when we do that. Now let's just keep going on here. Let's actually increase the number of samples. Let's do 100 samples of size 10 and let's see what happens. So look at this distribution. You can see that the mean is getting quite a bit closer. Let's do another 100, another 100, another 100. And as we just keep on sampling, which this would take a lot of time, or it would take a lot of students doing this, as we take more samples, we're noticing how that mean is steadily getting closer and closer to the actual mean, okay? So you should be looking right here at this value, this number, trying to show, and I'll scoot down, trying to show that it's going to be equal to the true population mean, okay? And it is just steadily getting there. We've done 5,213 samples. So we're going to write down some rules, okay? First rule is this right here. I put a little bullet point even in your notes. We're going to say rules for sampling distributions of X bar. So bullet point here, you're going to write this, right, just this part right here. The mean of the sampling distribution will be equal to the population parameter, the population mean, okay? That is the rule. So we can just write this. We're going to simplify it today. Okay, we're going to keep things nice and short and simple. So we're seeing that no matter what, if I reset this and start going again, any type of sampling distribution that I create is going to eventually have the mean equal to the true mean, okay, or it should, as long as I am sampling correctly. That would not be the case here because there's bias, right? But if everything's done properly, the mean of this should be equal to the mean of this, right? So if not, then you have bias. Something is bias, okay? So that's our first rule. Next, we're going to talk about standard deviation. That's what we want to do next. So I'm going to do several more samples here. So let's talk about standard deviation. Let's draw another bullet point. The standard deviation should be equal to this right here. Okay, standard deviation of X bar is equal to sigma over the square root of n. Do we know what sigma is? Sigma is the population standard deviation, which we actually know what it is in this case. And a lot of times in real life, like with the pennies, we would not have been able to know this, right? There's no way for us to know the population standard deviation. We have the simulator that works, but we have a population standard deviation here of 2.119, okay? Now, we also have to write this. As long as the 10% condition is satisfied, then that's fine. So what does this 10% condition do? We wrote that down last lesson. It shows independence. Shows independence. That's what that does. So that has to be the case. Now, let's talk about our situation here. Because we're going to calculate the standard deviation. Let me let's pull this up. We're going to talk about this. So if I wanted to find the standard deviation right here, because they actually calculate it, I can use this formula, sigma over square root n, okay, is going to be equal to that standard deviation. All right, but what is this formula saying here? N less than 1/10 of big N. So we need our sample to be less than 1/10 of the population. Well, we actually know the population. It's 268, and that's over there. Okay. So is 10 less than or equal to 1/10 of 268? Well, 1/10 of 268 is going to be equal to 26.8. So the largest sample that I can take is going to be 26. That's the largest sample for it to maintain independence. So what this really means is this. Look at how many words there are that are bigger than 8, that are 8 or larger, right? Or 9 or larger. I don't really know it. This is 9, 10, 11. Okay. If I take a sample larger than 26, it's very possible, or it is possible, that I could grab all of the large words, and now the probability of getting an 8, 9, or 9, 10, or 11 goes to 0. So we lose that idea, or that we lose that independence, because the probability is changing as I'm grabbing these, the probability that I get an outcome. Same thing with the one-letter words. There's not that many of them in this address, okay? So that's one of those reasons. So once we show that our sample size is small enough, we can use this formula here, okay? So I do want you writing this, by the way, and you can put example Gettysburg Address. We'll have our standard deviation. Our standard deviation should be, well, we take the population standard deviation, 2.119, divide it by the square root of n, which n is our sample size, 10. So we put 10. So we can grab our calculator. And let's do this calculation. We're going to make a fraction. We have 2.119 divided by square root of 10. And I want you to notice how close this is to this right here that I have on the screen. Okay? Which I have just blocked. It's very close though. Very close. And if I kept sampling, so let's do that. Let me go back to it. Let's take some more samples and watch the standard deviation change. It's eventually going to get to, let's actually raise this up to 1,000 at a time. Okay. It is eventually going to get to 0.67. Okay. It seems like it's a little bit off though. It has a ways to go with that standard deviation, but it would eventually get there. Let's do 10,000 at a time. Yeah, okay. So we have like 108,000 samples happening here, okay? Okay. So on the last, in the last section with the proportions, we were interested to see if the sampling distribution, so look at this one here, ended up having a bell-shaped curve. Is it normal? Because if it is, then we can do normal calculations. Well, let's overlay a normal distribution to this. So is our distribution approximately normal? Not really. If you look at it, it's slightly skewed to the right. You probably see that, right? Well, we remember this. If we increase sample size, it should help us alleviate this. So let's try 15 words, and I'll go ahead and do 100,000 at a time, if my computer can deal with that. Okay. So let's do a couple more 100,000 samples here, which I'm trying to make it to where y'all can see and look at it. So here's 300,000. Oh, okay, 600,000, and you can see it's still just slightly skewed to the right. Like it's not really getting a nice shape here for this, which I think my computer's going to break. Okay, now it's good. It's not really fitting this normal distribution. Let's go up. But remember, what's the largest size that we can have? Well, we said 26, so we're going to try 26. I need to like completely refresh this page because it's taking forever. Here, hold on, I'm going to skip ahead. Oh, no, here it is. Okay. All right, so let's try, let's do, I still want to do 100,000. We'll do 10,000 at a time just to make it easy on it. Let's do size 26 samples. And let's go ahead and start sampling a ton here. Okay, we're noticing that that mean is going to work out fine. We start looking at this distribution though. I mean, it's starting to get better, obviously, but at 26, it's still just slightly skewed to the right. Like, it's still not perfectly symmetric when we look at this. I mean, it's better, don't get me wrong, but there's still more, it seems like, out here than there are, you know, inside. Okay, let's draw a few more samples on here. I think we got it. Yeah, it's still just not, it's not perfect, okay? But we know we can't draw any samples larger than that. But let's see what happens if we actually do. Let's do 30. We'll draw these samples. That one's still not looking too great, but it definitely is the best one we've seen. Let's go to 50. Now we're losing that idea of independence, right, when we do this. But it is starting to become more and more normal. But this one here should actually be normal if we kept going, okay? Because the sample size is large enough to get us that shape, okay? And if we just kept going, let's increase this to 100. We're obviously definitely breaking the rules for the independence, right? Here's what all the samples are looking like, by the way. They're all skewed to the right, but the distribution itself is turning out pretty symmetric here. Look at that. That's actually the best one we've seen as far as the symmetry goes. But is it independent? No. Okay, so there's that. You can see where all the points are coming from here. I'm also going to link this app in here for you guys to play around with if you're interested in it. Okay, so we're gonna find a rule for this, by the way. Oh, actually, there's a couple more things I want to talk about before we write anything down. What's gonna happen if my samples are the same size as the population? What would the sampling distribution look like? Well, let's draw those samples. You'll notice that the sample itself is the population, so it looks identical, right? And then look at the distribution. It's just stacked up because every mean is going to be exactly the mean, right? So that's why the sampling distribution looks like this. Everything's just stacked up. There, it's 10,000 means of 4.295. It's 10,000 of them stacked up. Okay, so that is what that distribution looks like. All right. And then what's going to happen? Let's take a really small sample. Let's do 3, and let's draw the samples. Now what you're noticing is this one is, well, hold on, you can't see it yet. This one is harshly skewed to the right, and it's going to look a lot like our distribution over time. The reason that is because look at this sample here. It has an outlier almost, like 10. There's not a lot of 10s in the population, but in this sample we got one. It's causing that mean to shift up. Look, 5.33 was the sample mean of that one. And that's just going to happen when you get high outliers. Let's draw another sample, another 10,000. This one was kind of close, but overall, when we add these to our distribution, you're just making something that's skewed to the right because you are going to have some samples that are going to have those outliers, okay? So if the sample size is not large enough, your sampling distribution is going to end up turning out to look like the population distribution, okay? We have a property right here called the central limit theorem. So you wrote down these bullet points here. So what I'd like you to do is add one more bullet point right here, okay, for your rules. When the sample is large enough, the distribution of the sample means is very close to normal, no matter what the shape of the population distribution has, as long as the population has a finite standard deviation, okay? So here is the last part here. Central limit theorem says when n is large, the sampling distribution of sample mean is approximately normal. So that's important for us, like very important. This is one of the most important ideas in statistics. And if you take another stats class or a more advanced class, this is something that you're expected to know about when you, here, and I'm my camera up. This is something you're expected to know about when you're entering in that next level stats class. Central limit theorem is a big idea, okay? A big idea. So I'm going to pause and make sure you have that written. And then we need to also write, so there's a lot to write about this, but we're going to write this. If the population distribution is normal, then so is the sampling distribution of X bar. This is true no matter what the sampling size is. So before we write this, if I go back here, if this sampling distribution had been normal, then it wouldn't have mattered how large the sample was. If I took samples of size 3 or 100, the distribution would always be normal. But if the distribution is skewed in some way, then I have to take samples of size 30 or more, which is what central limit theorem is saying. N is greater than or equal to 30, right here. If the population distribution is not normal, the central limit theorem tells us that the sampling distribution of X bar will be approximately normal in most cases. This is actually better to write. I don't know if you've already started writing the other thing, but this is actually better to write for your rules, okay? This is better to write for your rules right here, these 2 points. So this is what you're going to write, and we'll pause and let you do that, okay? The other one is saying the definition and all that, but this is saying what we want it. This is going to be worded the best here, okay? So central limit theorem, I'll pause and let you write that. Okay, so why do we care if it's normal? Well, if it's normal, we can do normal calculations, which is going to be what the what the test is going to be over, your next test. So let's go ahead and look at an example in the problem set. That's what we want to do. So I've got my problem set up. We're going to look at number, and again, all of this is in Delta Math now. So you should be able to, before this lesson, you should be able to work 1 through 30. But now we're going to be able to answer these questions down here. And I'm going to be doing number 35. Okay, 35 and 36 are what we're going to be working on. Okay. So let's go ahead and answer these. I'm going to write on this. So it says, an automobile insurer has found that repair claims have a mean of $920 and a standard deviation of 870. Suppose the next 100 claims can be regarded as a random sample from the long run process. So this means this is N right here. All right. This is the true mean. All right, this is the parameter, and this is the standard deviation of the population. So these are all population parameters here. And now we're going to say the mean and standard deviation of the mean of the next 100 claims. So this is the sampling distribution. If I take a sample of 100 claims, calculate the mean of that, and then we start building a distribution like we did with the words from the Gettysburg Address. What will be the mean of that distribution, and what will be the standard deviation? So first off, the first rule that we have, which is the easiest one, is that the mean of your sampling distribution will be equal to the mean. So we know that the answer to this first part of this question, mean of that sampling distribution mean, should be equal to this 920. So it's not going to be C and it's not going to be D for sure. Okay? Then we just have to find the new standard deviation. Remember the formula for that. Sigma of X bar is equal to sigma over square root N. Now, because we have this none of these answer here, we need to make sure that we are actually allowed to calculate the standard deviation. Remember how we did that? Well, we had to check the 10% rule for independence. If I'm not allowed to, if this isn't true here, if this is not a true statement, okay, if that's not a true statement, then we cannot proceed. So the sample is 100. Is that less than 1/10 of N? Well, what is big N? Big N is the population size, okay? So what is our population size here? It doesn't really say, but if we can imagine this, it's an automobile insurer. How many claims do you think that they've reported? Well, we won't say infinite, right? But a lot. And we'll actually say this. I mean, we can basically put infinite, but we're really going to say this is sufficiently large. I'm sure I'm going to spell this wrong. Sufficiently large population. The population is sufficiently large. So we're going to go ahead and do our calculation because of that. So sigma, we know that's 87 or 870. We're going to divide that by square root of 100. And a lot of you could probably do this without a calculator, but obviously we can use one here to help us. 870. So we're going to do that. We do 870 divided by square root of 100. That's 87. Okay, 87. So A is going to be the best choice for this one. Okay, A is the best choice. This was 920, and this is $87. Okay, so we got that. That looks kind of bad. Hold on. Okay, so we're good on that. Let's go ahead and answer 36, and then we'll be done with this video. It's at 36 minutes here. Okay. So the probability that the mean of the next 100 claims is larger than 1,000 is approximately, well, anytime in this chapter, by the way, let me go ahead and say this. Anytime you see the word the probability, this means you're going to be trying to use normal calculations, Normalcdf, to find these probabilities. So that means we have to assume, or we have to confirm, that the sampling distribution will actually be normal. Okay? That's what we have to do. We have to prove that it's normal before we're actually able to answer this. How do we prove if the sampling distribution is normal? Well, we had these rules that we just wrote down. So if the population distribution is normal, then so is the sampling distribution. Okay, this is true no matter the sample size. So we go back here. Does it say anything about the population distribution being normal? And we read this and it doesn't. Okay, so we can't use that rule to prove normality. If it said in the problem that the population is approximately normal or possibly normal, we would say that. So that we can't use this first bullet point to prove normality. Next. This bullet point will probably help us. If the population distribution is not normal, or we don't know, right, not stated, the central limit theorem tells us that the sampling distribution of x bar will be approximately normal if, and we have this rule here, n is greater than or equal to 30. Okay, so is this normal? Well, n sample size is greater than or equal to 30 because n is 100. So because it's 100, it should be approximately normal. So now we're able to do Normalcdf. So in your calculator, go ahead and pull that up. Menu 5, 5, and then 2. That's what you have to do. So 5, 5, 2 to get your normal calculations. Okay, Normalcdf. So it wants the upper. So I'll just show this on here. Lower, upper, mean, and standard deviation. So what is the lower boundary? Well, let's read the question again. Probability that the next 100 claims is larger than $1,000. That's what we want. So we're going to put 1,000 in here. What do we put for the upper boundary? What would be the highest possible value? Well, we don't really have a limit for that, so we use infinity, which is going to be 9. We hit this double E, 9, 9. Then we go down. We're going to enter in the mean that we found from the first part. That 920 goes here. Then we're going to enter in the standard deviation that we found from the first part as well. So 87. Hit enter. There we go. So we should have our answer 0.1789, which is this is the one it's closest to. So we're going to go with C, and C is the right answer on this one. Okay. So that's what a lot of these questions are going to look like on here. And now at this point, the next week, we are just going to be doing a lot of practice. It's very likely that in maybe next Friday or maybe the following week, we're going to take our test over this unit and then move on to the next section. But we've done very well with this. or at least getting through it. So now it's just time to practice these problems, okay? And I know distance learners, this chapter, and I've always been worried about this unit for distance learners ever since we started the year, because usually this topic can be confusing. But if you're confused about what's happening, that first video we watched with the guy that's talking about sampling distributions, it would be a good idea to go back and watch that again at some point, and get a little more perspective on what exactly is happening. But I do want to go ahead and tell you guys one last thing here, is that part of your next test is going to be matching up all the symbols to their proper names. So one of the things that I'm going to push out next week is this worksheet. I haven't decided if I guess I'm going to keep it like a worksheet. I think that would be fine. But here is something that you're going to have to be able to do. You're going to have to be able to name all of these symbols here. What do they mean? I think on the test, you'll have something like this, and you're matching the symbols to the names, okay? So last year, I had a student that created a quizzes, almost sort of like flashcards, but better, because it's more accessible, it's easier, you can do it on your phone, where you can practice doing this. So I'm going to show you all that. So on this quizzes, I'm going to put the link in here, okay? You just hit start, and it should, I guess y'all are hearing this. Hold on, what are y'all hearing? Oh, it has music. Hold on. So you can just go through here and your time. So which two factors prove that sampling distribution of X bar is approximately normal? So that's what we just said. The population of state is approximately normal, or n is greater than or equal to 30. So you can submit that. And you can actually sort of quiz yourself and practice going through here, okay? We look at this one. Which best describes the sampling distribution shown below? This is an unbiased estimator, okay? So you can practice all of these concepts that we've been doing. It's a fun way to do it, okay? And just sort of work on the skills. What is this symbol? This is, it doesn't say sigma, it's population standard deviation. So this is sort of like the test. You're gonna have to know all of these symbols, okay? In order to do this. So this is great practice. What is that? That's p hat. What does it represent? Sample proportion, okay? So that's going to be the idea with this, okay? That is going to be the idea with this. And so I'm going to link this into the, here, I can share it actually. There we go. I can link this to you guys so you can practice this on your own. And you can turn off the memes, the timer, whatever you want to do with that. So I'm going to go ahead and link that, and then we'll stop the video here.